Hello everyone, this is the 1972 USAMO problem 1. So the first step we do is we can assign some variables, and that would be P equals the GCD of A, B, and C. And then we have this really neat Venn diagram on the side to show us the factors of A, B, and C. So since P is the GCD of all three integers, then we can put P in the center, because it is shared by A, B, and C. And then we can also say that PQ equals the GCD of AB. And we can add to our Venn diagram by putting Q over here, because P is already shared by all three. But AB might have some other integer factors that are also shared other than P. And as you see here, this section right here, as I highlighted, you can see that this area is not shared by C, but it's still shared by A and B. So that is Q. And then following the same logic, we can do the same for PS equals GCD CA, and then PR equals the GCD of B and C. Make that a bit neater. Yeah. And then now we add back to our Venn diagram, so we can see that goes here, and then R goes here. Okay. The next step is to show that S, Q, and R, they are pairwise coprime. So for the set of three elements, any two elements in every pair, they will be coprime. So GCD of QR equals 1, GCD of QS equals 1, and GCD of RS equals 1. Okay, so intuitively this makes sense because as you see, they are separated in different sections of this Venn diagram. But to actually prove this, we have to use proof by contradiction. So we first start with the assumption that there is a common factor between, let's say, just without loss of generalities, choose Q and R. So then we say that Q and R share a factor, common factor, D, larger than 1. And note that D is not included in P. Otherwise, then we just don't even need D because we could just write it in our P. It's like a factor of P. So then we can say that D does not divide P. All right. Since D divides Q, that means that D also must divide PQ. And since PQ is the GCD of A and B, right? Okay, yeah. Then we can say that PQ must divide A and PQ must divide B. So then translating this by just like attaching this step, we say that D must divide A and D must divide B. So doing the same thing for R, we can say that, say this, separate this area and say this is R. So then R divides, let's see, yes, R divides PR, and then since PR is the GCD of B and C, then PR must divide B, PR must divide C. And that means R must divide B, and R must divide C. So what we get here is that D must divide A, B, and C. Also, one step I forgot here was that D also divides R. That was implied over here. They share a common factor D. So that means, as you know, D must divide B and D must divide C. So then we combine all four of these statements to get this one. This final statement that says that D divides A, B, and C. Okay. But we know that P divides A, B, and C. And also P is the GCD of A, B, and C. which means that there is no other integer larger than p that divides all three, which means that d must be within p. So d must divide p. That is implied. And here's the issue. We stated at the front, at the start of our proof, that d must not divide p because d is exclusive. It's something that only q and r share. Okay, that's our issue. By contradiction, this is impossible. D cannot divide p. But q also must divide p. So this is impossible, which means that since both can't be satisfied, then d does not exist, and q and r have a GCD of 1, which means they are coprime. And you do this entire process 2 more times for all 3 pairs. Okay, so now we established that they are pairwise coprime, S, Q, and R. Our next step is to write A, B, and C in terms of S, Q, and R. Okay, so let's go back to our Venn diagram. We see that A equals something times S, P, and Q. We can say this something over here is A prime. Okay, why does this make sense? We already know that A has the factors of S, P, and Q, but A also may have factors that are in this section here. This section is not shared by any other section. This is the area where all the prime factors only divide A, and they are distinct to A. All right, we can do the same for other zones, so we get P prime and C prime. Okay, so now we can get to the section here and then write A out. We can say A equals SPQ A prime, B equals PQR B prime, and C equals SPR C prime. Okay, very nice. And now we go back to our problem. It said we want to prove this, right? So we already have the entire right side because this equals P, and then we have this is equal to PQ, this is equal to PS, and this is PR. So we don't really care about this, but we still haven't done this section yet. So we do that right now. So first we need to find what the LCM, which is the least common multiple of all 3, A, B, C. Well, again, go back to the Venn diagram and we see that it's just all of these factors multiplied together. So this equals A prime, B prime, C prime, S, Q, R, and P. And why? Well, this is because all 3 sections have a combined number of factors that are all distinct from each other, and they all do not divide. They are all coprime from each other. So we can multiply it like this. As you see, they are not shared by any other sections, and they're very unique sections, and they do not share any prime factors. That is the main point. Okay, and then the same process we do for A and B. This equals, well, we can take a look here, and we see that to cover all the areas of A and B, we need this entire section here, which I'm going to highlight here. Yeah, we need this entire section. And that has A prime, B prime, S, P, Q, and R. So we write that A prime, B prime, S, P, Q, and R. And the same process goes for the other 2 pairs, sorry. And then we get BC equals C prime, B prime, S, P, Q, and R, and AC equals A prime, C prime, S, P, Q, and R. Great, now we can substitute everything back into our final expression, which is the LCM of A, B, and C squared over A and B, LCM, and then BC, LCM again, and then CA. What is this? Well, it's A prime, B prime, C prime, S, Q, R, P squared over A prime, B prime, S, P, Q, R times B prime, C prime, S, P, Q, R, and then move over a bit, and then A prime, C prime, S, P, Q, R. Great. And And now we can just do some algebra, and then we find that a prime, b prime, c prime squared times sqrp squared over sprq cubed times, you see there's two a's, two c's, and two b's. So we can say that it's just a prime, b prime, c prime squared. So this entire section cancels out, and this power cancels out too, remaining one exponent. So we get 1 over SPQR for this entire expression. Okay, on to the right side. The right side we have ABC, the GCD of ABC squared over the GCD of AB times the GCD of BC times the GCD of CA. And this, we can just go back to our previous notes to see that they are right over here. They are so convenient for our usage. We can just say this equals P squared over PQ times PR times PS. And what is this equal to? We can cancel the P's. 1, 2 equals 1 over QPRS. And what is this equal to? No way, it's the same as the previous expression. So we proved that this entire LCM expression is equal to this entire GCD expression. Circle these. Sorry for the bad formatting. All right, this problem is done. Hopefully you can watch the next video and learn something new. Have a great day.